Hi y'all, welcome back to another round of physics, and as you've noticed or as foreshadowed in the past video, today we're going to be dealing with the derivation of the kinematic equations using calculus. The next question, or at least as promised, that's the algebraic way. Why don't we go through and do it the calculus way? Okay? Dun dun dun, rubber hits the road. So if I'm doing calculus, I'm going to use the derivative notation, namely a is equal to dv dt. I set my acceleration equal, the instantaneous acceleration is the derivative of the velocity versus time. And now you might have seen this already in calculus, I don't know for sure. What I'm going to do is I'm going to move the dt to both the other side. So I'll end up with something that says dv is equal to a dt. And this is a very standard, I don't want to say trick, this is a very standard method in calculus. So what is called a separation of variables. Okay. And that's generally what you try to do. You get the dv on one side, you get the dt on the other side. And then we're going to do what's called an integral. You say, whoa, 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 what's going on here? An integral is just a fancy notation. Okay? Just like this, if you recall from the last couple of videos ago, we said, hey, let's take the limit as delta t goes to 0 of my strobe flashes. And as the limit as delta t goes to 0 of delta x delta t, that gives me my instantaneous velocity. And that, again, why were we trying to do that? We were doing that so that we have the most accurate picture of the motion of the object. If we can get our strobe flashing really, really fast, then we see where our object is at every single point in time, and that gives us a better idea of what the motion of the object actually is. Okay? So this is a limit as delta t goes to 0. Now let me, if we were talking graphically for a moment, you know that this looks like the slope. So if I have an x versus a position versus time graph, then the velocity is given by the slope of that graph. I calculate the slope, that's the velocity of the object. Okay? Now, you say, okay, well, how does that, what does this thing mean? Okay. And again, I'll go back to something that we've talked about, and the question is, if I have a speed versus time graph, how do I get the position? Okay, enough time? Pause it. Say, well, the question is, if you're driving at 60 miles an hour for 3 hours, how far have you gone? Right? So if I drive, say for example, I'll say 60 miles an hour, we'll say 60 for 3 hours, 3, put time in hours and mph. Here we go. How far have you gone? Excuse me. And the answer is you've gone 180 miles. You have taken the v versus time graph, the velocity versus time graph, and you have found the area beneath the curve. You multiplied 60 by 3, that's finding the area of this rectangle. Okay? That is what this integral sign is doing. It's a fancy way of saying, take the two numbers, multiply them together. Now the one trick is that it doesn't just do 60 times 3. It says, okay, well, let me go 60 times a really short interval, say 1 minute, and then I'll do it again, and then I'll do it again. So it's taking this velocity versus time graph, and it's chunking it up into really, really, really tiny pieces. You say, why are we chunking it up into really, really small delta t's? And that again goes back to the last video. We said if you have, this is for a constant velocity, but if you have some non-constant velocity, say, excuse my board work, say something like, this, how do you actually do it? Well, we've talked about it. if we zoom in really, really far, then our graph starts looking like a straight line, say like this. And then, as we talked about last time, I can find the area of that little trapezoidal piece. And then I do it again. So I say, okay, well, this is delta t. Oops. This is my small delta t. Boy, that's really fuzzy. My small delta t is right there. Okay? So then I do it again, and I do it again. So I have to do it a whole bunch of times. Let's undo that. So what happens is if I have a non-constant velocity, then I can chunk it up into really small time intervals and then find the area for each of those small little chunked time intervals. And then I have to, of course, at the very end, if I want to know my total, I have to add those all together. So this, if you ever see, when you see this integration sign, you're really just doing the summation of area beneath curve. It's mathematicians being lazy again. Conceptually, you hopefully feel comfortable with what's going on there. So let's go at it. Now, ideally, what we would do is you have a t and you have your a. And in the most general sense, you'd have some changing a. You chunk these up into small time intervals, You'd find the area, that one's not very good. You'd find the area for each of these little thin slices, and you go at it. But, and here's where our assumption comes back in, but to make this job easier for us right now, we are not going to do some kind of goofy rigmarole acceleration. What we want to deal with is an acceleration that is nice and constant. And so this is the kind of acceleration that we're going to deal with. And you know, if this acceleration's a and the time is t, you know how to find the area of that rectangle. This is just simply a times t. Over here, you know that this should give you the change in speed. Something like that. And you're good to go. This is one of the kinematic equations, of course. Now, the next step, if we want to go further, let's say, for example, we don't know what the final speed is. We know the initial speed, but we don't know what the final speed is. But we know how far it traveled. So the next step is, we'll call this some constant, some known constant. This one's unknown. So what we're going to do is next move this to the other side. We get v final is equal to at v naught, v naught. And instead of v final, we're going to now use the instantaneous speed, dx dt equals at plus v naught. Again, we'll perform separation of variables. I'm sorry, I'm getting low on the screen here. So we have dx, got overzealous there, dx is equal to v naught plus at dt. Now let's look at what does the plot of this look like for a moment. Let's go graphically again. So I keep going back to the graphical just because we're probably not as far along in the calculus yet that we need to be. So here's time. Let's plot this as time. And I will plot this as my speed, v. And what does this equation tell me? Well, this looks a lot like mx plus b. Here's the variable, the independent variable. Here's the slope. Here's the initial intercepts. So this would look like v naught, and then some sort of line at a slope that has a slope of a. So v naught, and this line has a slope of a. There's some final time, call that t. Good? Cool. But we've already done this situation, right? Do you notice that we've already done this situation here? Right? I mean, well, okay, we'll stretch that across. You can find this. What's the area of that going to be? Good. Just V naught times T, right? That's the area of this rectangle underneath. And then how about, what's the area of the triangle? One's a little trickier. You say, okay, I got this. I got this. Right? So the height here, this height, is simply just A times T. And the base is, again, just distance T. And so the whole thing, the area of this must be 1/2 AT squared. That's exactly what the integral will give you here. You'll get something that says, and we'll stretch down to the bottom, you'll get something that says x final minus x initial is equal to V naught times T, that's the area of the rectangle, plus 1/2 AT squared. And that should look familiar. That is exactly, this is a delta x, V naught T, 1/2 AT squared. Now I don't have the deltas in here, but that's what we wanted. This is what we called one of our first kinematic equations. And I guess I'm doing it with lines. There's one of our kinematic equations. Pretty cool, huh? No? Seriously? You're not excited about this? Really? I try. Okay. While we're at it, let's get the other one. Okay, let's go at this next one. And we're going to actually start off with the acceleration again. And I'll write it down, dv dt. And now we're going to do something which I guess mathematicians and physicists, we formally call this a dirty, rotten, stinking trick. I'm just joking. In all reality, we're going to do something here that looks both weird and easy, hopefully simultaneously. And the trick is, I say trick, the standard method is I'm going to multiply this equation by 1. But I'm going to do it in such a way to help me actually get through the rest of the problem. So right here, I'm going to actually, so we still have our a here, and I have our dv dt, and I'm going to multiply it by 1. But I'm writing it as dx over dx. You say, well, why? What are you doing? Let me rearrange stuff. So I have a, and now I will write dv dx dx dt. And hopefully now you go, ooh, sneaky. Because if I look at this for a second, you see dx dt, I know what that is. That's just my velocity. That's my instantaneous velocity. So I will write a equals dv dx times the quantity v. Now I'll go ahead and perform my separation of variables. I'm going to move my dx to one side. I'll have my v to the other. And we have something that says a dx equals v dv. Ta-da! Cool! Now, of course, a is constant. So let's go ahead. Now the next thing I need to do is I would like to actually do the integrations here. So I want to find the area beneath the curve. And if we look at how we did this last time when we were faced with a dt, what we actually did was first of all, let's do this. This, which was a dt, now it's a dx, but this derivative here, this differential, or I guess maybe it's not a differential, but this dx component, that tells you the independent variable. So the last time we did it, it was dt, time was the independent variable. Here we're going to use x as our independent variable. So that goes on the horizontal axis. And then this term right here will go on my vertical axis. So I'll put my acceleration. Now we're going to take advantage of the fact that our acceleration is constant. So if I have some constant acceleration, I need to find, again, the area of this rectangle, knowing that this is x final, this is x naught, and this is a. You say, okay, well, that's just I'll put delta x. Cool, we're done. That's half the battle again. And remember, just finding the area. So let's do the same thing for this side. And here we have to be, I wouldn't say careful, but we're going to follow kind of the same pattern. So we have, I guess, what we'll use as our independent variable is v, and we'll plot v also on the horizontal or the vertical axis, excuse me. So now we're at this interesting situation. We go, okay, I think I got this. And here's a question I should ask you. Okay, so we have v and v. And the question I should ask you is, what should the slope of this line be? Okay, good. Yeah, if this is v versus v, any change in v results in a change in v. So I should get a 45-degree line. Pretty cool. So I should get a line that's at 45 degrees. Something like that. Go like that. And then furthermore, let's see here. So I have a line at 45 degrees. It should end at whatever v final is. So we'll draw this. I'll draw this down to help us. But we start out at some speed, v naught, and we end up, sorry, I drew that axis too short, at v final. So now I'm thinking about how do I calculate the area here. We have this distance as being v final minus v naught. Like that. Now knowing that this line here is at 45 degrees, and we know that this height is v final minus v naught, you should hopefully understand or see that right here on the x-axis, we've gone a distance of v final minus v naught. Now, pause the video and convince yourself that you understand, or that makes sense to you. Okay. Oh, excuse me. So now we're in a situation where we can actually go through and find the area of this. How we do that? Well, I have v naught times a distance of v final minus v naught. So that's this, v naught, v final minus v naught. And here we have a triangle that has a height of v final minus v naught and a width of v final minus v naught. So as the area would be v final minus v naught squared. Cool. So we just have to add all of that together, right? That's what the summation is doing. So I have something that says 1/2 v final minus v naught squared plus v naught v final minus v naught. Take a minute, go ahead, pause the video, see if you can simplify that. Okay. Good. 1/2 v final squared minus 2v final v naught plus v naught squared plus, so I'll parenthesis that in, v final v naught minus v naught squared. And we see, aha, this cancels that. Don't forget about the 1/2 in front, right? 1/2 times 2, this, that. Those cancel. So this cancels that. And furthermore, I get a little bit more simplification. I've got a half v naught squared and a minus 1 v naught squared. So that gives me a negative 1/2 v naught squared. So at the end of the day, I end up with something that says a delta x equals 1/2 v final squared minus v naught squared, which is, of course, one of our kinematic equations. Of course, if you want, you can move the 1/2 to the other side. But that's it. That's the other kinematic equation that we were looking for. Good? Of course, on the way, we of course had the other kinematic equation right here. There's one. And we also had, we also used the other one. Where did it go? Well, yes, we also used the other one about delta x being v final plus v naught over 2, the arithmetic average times t. Okay. So I think that leaves us, I think we're good to go here with the calculus-based stuff. I think next video what we'll do is I'll run just a quick example on how to use some of these equations. See you next time.